All right, so just an announcement. Remember that last week was your opportunity to go to see a lot of employers, and hopefully you took advantage of that opportunity. If you didn't, then here's your second chance, or another chance for those that did. We have a School of Computing specific Connect to the Network run by CSAB. That's the Computer Advisory Board, so it's the student-led group that engages with industry and with us to make improvements to the program. Anyway, tomorrow they are meeting from 4 to 6 over in the Shore Center. That's the building on the south side of the stadium, so just over there that way. And it's on the second floor, and you'll be able to connect and network with several industry partners and folks that are looking specifically for computing folks to hire as interns and for full-time employment. So I would highly recommend that you make your way over there. There will also be plenty of free pizza, it says. So no need to bring your resume or dress up. Just stop by. But I would still bring your resume and cover letter if I were you. All right. So just to I need to refresh over here. All right. So just a review of what we did last year or yesterday or Monday, whatever it was. A pointer is a memory address, right, or a reference. A pointer can be declared using that star syntax right there, right, the asterisk. It's best practice to initialize it to null unless you know exactly what you want to point it to immediately. Then you can do, later on, you can do null pointer checks. To make a pointer variable into a regular old variable, you dereference it. So you use another star, right? To make a regular variable into a pointer variable, you use the ampersand, the referencing operator. Don't make pointers point to things that they shouldn't, okay? Remember, I think I mentioned it, but which one is which? You just have to put this up on a Post-it note and put it up on your desk until you've driven it into your brain. The regular old variable changed into a pointer, that's going to be ampersand. A pointer variable into a regular old variable is a star. Once again, let's see this in action, but let's go ahead and use Python Tutor here in order to see what visually what everything is going on here. Here's my regular old variable that I'll set equal to 42. Okay. Then I will create a pointer variable, p, and I will not initialize it at all. Right. Later on, I'll initialize it to null. Okay. And then later on, I will again initialize it so that it is actually pointing to a. Now, is that correct? Nope. The thing on the left-hand side is a pointer. The thing on the right-hand side is a regular old variable. So what do I do to that regular old variable to make it into a pointer? Ampersand. Okay. And then you can change it through the pointer. So if I say p is now equal to 52 instead, right? But that's also wrong. The thing on the left-hand side is a pointer variable, so I'm basically making it point to memory location 42. What do I have to do to take a pointer variable and dereference it so that it's a regular old variable and I can set it equal to 42? Star. Once again, let's go ahead and visualize this execution, and you'll actually see what it looks like with the pointer. All right? So I initialize a to 42. And by the way, what is p pointing to before I set it to null in line 8? Question mark. Right? Usually they have like a skull here, right? When to indicate that it's a dangerous thing, it's uninitialized memory. But in this case, I don't know why it's just showing up as a question mark here instead. So we'll go ahead and set it equal to null, right? Null. And you'll see here that that address is 0. Again, do not treat null as 0 and 0 as null, right? Don't conflate the two. Use the keyword null there, okay? Now I'm going to make p point to a. See that? Now it's pointing to this variable up here, right? That's what it's doing. Then I can dereference it, meaning that I will jump to that memory location and reset the value equal to 52 now. Right? So pretty straightforward as long as you're keeping it simple. Why do we need this? If I just got a regular old variable, who cares, right? Why can't I just go ahead and use it? Well, it opens up the door to passing by reference. Recall that passing by value means that copies of the variables are passed to the function, right? So for example, let's come back over here and edit this code, and I don't have it set up, but you remember that we did this swap demo? Int a is equal to 10, int b is equal to 20, right? And I'll call this swap function. that swaps A and B. And then I'll print it out before and after. A is equal to %D, B is equal to %D, and the line, A comma B, right? There we go. And I will print it out before and after. Well, of course, I need to write the swap. So void swap int A, int B, right? And I'll create a temporary variable here. I'll just call it T, and that takes on the value A. A takes on the value B, and now that A has been copied, I can say B is equal to that temp variable and return. Again, visualizing this execution, we'll see that copies of the variables are copied onto the call stack. So it's 1020, right? A new stack frame is created. That AB in that swap stack frame is not the same AB as in the original stack frame in main. So when I swap them, I'm swapping them in the swap function, the copies. Right? When I come back and that's destroyed, 10 and 20 are unaffected. So what I want to do now is I want to change this so that it's pass by reference instead. Right? Pass by reference means that memory addresses, or i.e. pointers of variables, are passed to the function instead of copies. Right? That means that if I've got memory addresses, I can jump to those memory locations and manipulate the contents of memory directly. Let me go ahead and do that. Edit this code, and I will copy paste this just so I have the other copy, but pass by reference, right? Swap by reference. Now, int A is a regular old variable. How do I make it into a pointer variable? This is the declaration. This is a declaration, so it's not like ampersand that gives you the memory location of that. It's like declaring a pointer, right? Int star A, int star B. Now they're being passed by reference. In other words, pointers to integers are being passed in there. Right? I'll go ahead and keep the regular old variable T here, but how do I get the value stored in A? A is now a pointer variable. How do I take a pointer variable and turn it into a regular old variable? I dereference it. Likewise, dereference, dereference. But let's think about that first. A is equal to B. The thing on the left-hand side is a pointer. The thing on the right-hand side is a pointer. So they're compatible. What are they actually doing? It's just making A, which is pointing to that memory location over there. Now it's pointing to the memory location of B instead. Right? So I don't want to make the pointer change. I want to make the contents that the pointer is pointing to change by dereferencing them. And finally, dereference B, oops, to put in T, and then return. Now let me change it down here, swap by reference. Okay. Now, when I call that function, A and B, the copies are not sent over there. There, now I've got the skulls, right? All right. So, oops, no. Why? Okay. What's wrong? We'll find out here. Did I do something wrong that it compiled? Why did it jump ahead like that? I have no idea. Anyway, 10, 20. All right. Print them out. Now we're going to call that function. Instead of 10 and 20 being copied into the new stack frame that's about to be created, 2 pointers are passed. And they reference, oh, good. Yeah, I did make a mistake, right? Why are they death heads here? Why are they skulls? Let's go ahead and go back and edit this. This would have come up if I used the wall flag, right? So swap by reference. It expects what? 2 pointers. Swap by reference down here when I call it, are A and B regular pointers or they're regular variables? So how do I take a regular variable and make it into a pointer? Ampersand. Ampersand. There we go. Now they won't be weird skulls. All right, so fast forward here. There we go. And now they're pointers to A and B. So that when I pull out the temporary variable there, I'm jumping from that memory location to where it's actually stored, and I'm getting the actual value 10 now. Likewise, I'll get put B into A and then A into B. Now the original ones in the main stack frame are being manipulated. Right? Next, next. So when I come back, now they are properly swapped. Right? Well, it seems like a lot of work just to swap two variables, right? Why would you need to do this at all? Right? Because it has the following benefits, right? You can now return multiple values from a function. And I'm not putting that into code, I'm putting that into quotes there. Think about what you did in your lab yesterday. You had this 2sepia function, right? In fact, you had to have 3 of them because you had to have one for the red value, the green value, and the blue value, right? Red, RGB, red, green, and blue, right? What if, and you'll do this next week, what if you could return 3 values then instead? In other words, you didn't have just one function, or you didn't have 3 functions, you had one function that returned all 3 RGB values at once, right? That would be much cleaner code. Let's go ahead and demonstrate this over here in our original, I'll just go back to our C stuff over here, right? And in the right class here, there we go, there we go. All right, now I believe we did it at some point, but remember that we did the quadratic equation, right? And I don't know if we put it into functions or not, but let's go ahead and see what it would look like if we did put it into functions. Double get root 0, 1, right? And we'll take in double A, double B, double C, right? Those are the coefficients to a quadratic formula. Well, that's only one root. I would also have to do get root 0, 2, or get the first root and get the second root or whatever, right? You'd also have to write documentation here. Let's come over here and see what it would actually look like. The first one would be, what? Return negative b plus minus, so we'll do the plus on this one. Square root of b squared minus 4ac all over 2a. And I need a numerator there. And I've got my denominator and we're good. Right? Copy, paste. But instead of the plus, I'll do the minus. Right? Okay? That's if I'm stuck in a world where I only have pass by value. What would it look like if I had pass by reference instead? So I'll call this compute roots. Right? Well, first of all, I'm no longer returning something. Right? Instead, what I'm going to do is I'm going to return something in 2 buckets. When I call this function, I'm going to pass it 2 buckets that I want filled. The first one with the root and the second one with the second root. Right? Those buckets are going to be pointers. Double star root 1, double star root 2. Right? So by passing in 2 values by reference, now the function can actually manipulate them. And it can return, right, in effect, 2 values at once. What would it look like? Let's go ahead and compute this now. Well, I don't return anything, so I'll just say return right there. I need to compute the first root. Double root 1 is equal to, I'm going to go ahead and grab this. Actually, I could call that function if you really wanted to reuse it, but I'll do a cut and paste here. And a root 2, double root 2. Actually, I've already used those values, right? So A, B. Should I even be declaring variables here? Well, if I've already got root 1, let's go ahead and set it. I've got root 2, let's go ahead and set it. Careful. The thing on the left-hand side is a pointer. The thing on the right-hand side is a number. How do I take a pointer and make it into a regular variable so that I can assign it a value? Dereference it with star and star. Okay? Now, I don't return anything. Instead, I have 2 buckets and I filled those 2 buckets. I don't return the buckets. You gave me the buckets, right? These are buckets that we're sharing. They're basically a memory location. Okay? Compute roots. Let's look at this as a demo here. So that's all in the notes. You don't need to copy it down or anything. It's already in the notes. So let's go ahead and create these variables. Double A is equal to, I don't know, 10, double B is equal to 20, double C is equal to 30. Is that going to be okay? Let's make this 10 because I don't want imaginary roots. Right? And let's go ahead and create two variables here for roots. So double root R1 and R2. Okay. Now I want to call that function. I'm already including the math library here. So let's go ahead and compute roots, passing in A, B, and C. Those are all by value. Copies of A, B, C, 10, 20, and 10 are going to be copied onto the stack and provided to the function. R1 and R2. Remember, what was my mistake before? These are regular old variables. They're expecting pointers. So let's give them pointers. Regular old variables into pointers are going to be ampersand. Printf roots are going to be %f and %f. And the line, R1 and R2. Okay. Let's go into lectures, GCC -C, mymath.c. Let's turn on all the warnings as well. Great. GCC mymath.o, then demo.c, and link in the math library to produce an executable file. Oops. Did I screw something? Return 0. Yeah, what did I forget? There we go. All right. And I have no idea if that's correct or not. -1 and -1. Wolfram alpha, how do you find that out? All right, 10x squared plus, I said 20x plus 10 equals 0 roots -1 and multiplicity 2. So yeah, okay. I had a hard time believing that, but fine. All right, so it is correct, right? Okay. So think about how you're going to do your lab next week. Instead of 3 values, and that's, you should retain your code from this week because you can do a lot of copy paste. But instead of 3 values for red, green, and blue for sepia, now what you can do is you can simply just have one function that does all 3 at the same time. Okay. Here's some pitfalls. One of the common mistakes is, oh well, it expects roots. It expects pointers. I'll just go ahead and make these pointers immediately so that I don't have to have an ampersand there. Okay. Well, tell me, as of line 15, what are R1 and R2 pointing to? Remember, that's that skull thing, right? Or the question mark, right? I have no idea. Dead beef, right? It could be null, and if it is null, then what's going to happen when I try to dereference it over here, right, like this? Let's find out. So I just have to recompile. Yeah, I'm getting a warning now because I should not be doing that. But as a consequence, it's just warnings. You can go ahead and do it. I think it might have said this before, but Java is a language that if you try to do something illegal or stupid, if you try to shoot yourself in the foot, it's going to say, well, I don't think you want to do that. Java will. And C is just going to simply ask you, what caliber of gun do you want? Right? Go ahead and shoot yourself in the foot. I don't care. Right? I'm going to warn you about it, but there you go. Go ahead. Segmentation fault. Right? Why? Because what I'm doing here is I'm dereferencing an invalid pointer. What is it pointing to? I have no idea. If I set it equal to null, now certainly it's obvious that those are incorrect, right? Because it's pointing to nothing. And dereferencing nothing means that you can't put anything into that bucket. The bucket doesn't exist. And once again, I'm going to have a segmentation fault here. Right? Again, what I'm doing here is I'm taking a null pointer in compute roots, right? And I'm trying to dereference it, but that's null, so it's illegal. Now there's a nice little, not a mnemonic device here, but there's a nice little device here that you can remember about this by asking, does anybody know who Bret Hart is? Nobody, I don't watch wrestling either, but he's an old wrestler from the 80s and 90s, right? In the 90s, there was this game that they were producing, right? Oh, you've seen this? Okay. There's this game that they were producing for WWF or whatever it was, and as a promo, they had all these wrestlers come in and interact with the developers. And I don't know if this is going to play on the speakers in here or not, but I'll crank my speakers.
Come on, you guys. There it is, right there in front of you the whole time. You're dereferencing a null pointer. Open your eyes.
There you go. So, nobody laughed at that yesterday in the main section, right? Of course, next time you have a segmentation fault, you're probably dereferencing a null pointer. Hit yourself upside the head and then go back and fix it, right? So that's a nice way of remembering that you can't do that, okay? So now we can return multiple values, right? Simply returning a value by using a pass by reference means that you don't have to explicitly return a value. This frees up the return variable. Void, right? I'm not returning anything anymore, am I? Seems kind of a waste though, right? With that return variable, we could do something. We could do something called error handling, right? So now in main, when you exit with an error code, 1, 2, 3, 4, right? Or when you return 0 at the bottom because everything was correct, now what you can do is you can start writing your functions so that you return an error code, just like that, okay? Before we do that, though, let's talk a little bit about Java. Right? So, Java, are there pointers? Not really, right? In fact, C and C++, and I guess maybe Rust to an extent, are the only languages that I know of that have actual pointers. PHP does allow you to do pass by value or pass by reference, but there aren't really pointer variables. We call them first-class citizens in a language. Like int, that's a first-class citizen because it's built into the language. Int star, it's built into the language, right? What would happen if we tried to do the swap demonstration over here in Java, right? So for example, int a is equal to 10, int b is equal to 20, and I'll try to call swap here on a and b. Right? Now obviously they are not going to, it's not going to work here, so I'm not even going to bother printing them out. But let's look at what it would look like. Public, static, void, swap. And I'll go int a and int b. And int t is equal to a is equal to b is equal to a, and then return, okay? And I'm not even going to bother printing them out here. Instead, I'm going to remind you that we have this debugger that we'll be talking about in a couple of weeks. I'm going to run the debugger so that I can step through it just like I would with Python Tutor. It's not going to be as visually stimulating or whatever. Come on. All right, I don't know why it's not running, but, oh, it is. I'm already in the debug mode? No, I'm not. All right, run it once at least. Oh, wow. My Eclipse is totally screwed up. All right, fine. We'll take...
Is it the debug symbol at the top right up there?
It's right, I guess, but it's not running at all. Like, okay, run. Okay, because I don't have, there, I don't have a, it was running. It was just running immediately. I didn't have a breakpoint here. So there we go. So there we go. It will run up to that point. All right, now let's go ahead and step through it. A, B. Let's go ahead and step into. Now instead of hitting the same button I just did here, I'm going to step into that function. Otherwise it would just step over that function and execute it all at once. Let's step into that function. All right. Now I have variables A and B here, but and it's not going to show it, but those are different variables now. A, B, and then return, and then A, B is still 10 and 20 here. Right, that's all I wanted to show you. Now you might think, well, wait a second, don't we have these other things, big I integers? And we do. Big I integer and big I integer. Terminate. Hopefully it terminated. All right, there we go. And let's go ahead and change that, change that, change that. There we go. Terminate, yes, terminate. All right, there we go. All right, so those are basically references. Right? At the end of the day, it's an object that is stored in memory. The object itself is a reference. You can, in some ways, you can get the memory address, but you can't manipulate it directly. Java doesn't let you do that. So even though these are references and it's being passed by reference, why can't I change it? Basically what's happening is I'm changing the references. I'm changing the pointers. It would be like if I had this exact same straight code with pass by reference in C. I'm making that thing point to that thing, and I'm making that thing point to that thing. But the original A and B, the values are unchanged. Let me show you. There is a Python tutor for Java. There we go. And let's go ahead and edit this, blah, blah, blah. Go all the way up here. Ooh, do I need, okay, so what do I need? Oh, I need, okay. I think, do you end right there? Okay, you end like right there. All right, you know what? I'm just gonna copy everything. I don't know if it likes packages or not though. So let's visualize this. All right, we are going to have stack frames here now. A and B in main. Now when I call swap, now unfortunately it's not real, darn it. I expected it to actually make a reference up here, but it's not, so be it, right? And then 10 and 20. Right? Anyway, I wanted it to be a little bit more visually appealing there with actually referencing it. The reason it's not working though in the main is because it is swapping the references, right? Even though they are technically references. The issue here is that in Java, objects, say integer, big I integer, double, string, etc., are technically references, right? They're technically references to the object stored in memory. However, in Java, all of these types are immutable. Do you remember immutable? We talked about that with respect to strings, right? The string, a string is immutable. Once you create a string, you cannot change it, right? We'll talk about strings more in more depth later on, but basically immutable means you can't change it. Once I've created A and B, 10 and 20, A and B, I cannot change those. I can't swap this out because I cannot change the value that's stored in A. Right? So what happens when you're actually, swapping these things out, right? Let me go ahead and simplify it, and we won't even have a swap here anymore. Integer A, and then I'll say A is now equal to 20. Right? I am not reassigning the value here. If it were a primitive type, int, a small I int, I would actually be manipulating the contents and changing that. Right? But in this case, I am not changing it. What I'm doing is I'm creating another variable called A, I'm creating another variable with a value 10, and I'm making A now point to this over here. Right? That's what Java is doing, because you cannot manipulate the contents over here because it's immutable. So it's something slightly different, and it is something that you need to understand later on. But just understand for now that there are no pointers in Java, right? So you can't do any of this stuff in Java. There is a mutable. What is the mutable version of integer? Java mutable integer. Come on. Mutable int. Okay. Oh, no, you'd have to bring in a library to do it. Apache's common language library. There's nothing built into Java. There is a thread-safe version of an integer atomic int that you can manipulate, but we won't get into that at all. Right? So and just to know that you can't. You're actually creating two variables here in memory. Two integers are created. Right? The reference A is being changed. And what happens to that original A now that A is no longer pointing to it? Because A was referencing this thing, we destroy that, and now we reference this thing over here. What happens to this? Automatic garbage collection. The Java virtual machine will see, all right, nobody's using that, so that's a candidate for cleaning up and reclaiming that memory later on. Right? And it does it at some point. Right? I'll put that small little snippet over here in your notes. But otherwise, that is functions. Any questions on functions, methods, et cetera, et cetera? Then let me give you a preview of what we're going to do next. What we're going to do next is error handling. Okay? Let's go back over here to C. There we go. Now, lots of things could go wrong here. You tell me, what's one thing that could go wrong? when computing a quadratic formula. Negative b plus minus square root of 4ac all over 2a. Yeah,
The square root can be negative.
yeah. If this thing right here, we call that the discriminant. There we go. Thank you. I was thinking radical, but no, it's a discriminant. Right? If that's less than 0, 0 is fine, by the way, right? Because the square root of 0 is defined and it's 0. Right? So if that's negative, then error. Right? What's another thing that could go wrong? Hey, divide by 0. A is 0. A different error. Right? There we go. Is there anything else if, sorry. Is there anything else that could go wrong here? Bret Hart, is there anything that could go wrong? Else if A is a null pointer, or not A in this case, sorry. What is it, root 1 is a null pointer? Or root 2 is a null pointer? Then another different error, right? Otherwise, we can go ahead and take care of our business and put the values in the buckets and be on our way, and then we can return. Because we've freed up the return type here, we can now communicate that error, which type of error or no error, to the calling function. Instead of returning void, I'm going to go ahead and return an integer here. Now, if it's this type of error, I will return, I don't know, 1. Actually, let's just make up a number. 123 there. I didn't mean to mash it all in. 13. There we go. All right. Now, if it's this other kind of error, I'll return a different number. I can't return 13 because that would conflate the two errors as being the same. So I'll just go ahead and go with 38. Okay. And if it's this other different type of error, then I'll return 37. Right, something like that. Now, if there's no error, what should I return? What's the universal sign for no error? 0. Right. Was there an error? True or false? False. So I return 0. Right. Otherwise, was there an error? Yes, yes, and yes. And depending on the value, you can actually capture that value and then handle it somehow. If I receive an error code of 13, I'll go ahead and do this. Otherwise, if I receive an error code of 38, I'll do that. Right? Yeah, go ahead.
If you were to use a function where you're actually returning the value you computed, how would you have errors there?
You can't. So, for example, well, we'll talk about that later. But for example, square root that returns a double and takes a double. It doesn't take anything by reference. So the way that it does error handling is it has this other library called errorno, and then there's this flag that gets set, and then you can check that flag if you want to. But with respect to functions and designing functions, you can design a function with no error handling. Right? That's what we've been doing up to this point. But now we're going to start designing functions that do have error handling, meaning that we're going to have to use pass by reference to return the actual values, but then the return type to return an error code here. Right? Now over here in the demo, we can go ahead and capture that. Right? I don't even need to capture it. Right? If I choose not to do error handling, then I can just move on with my life here. Right? It won't work, but it won't crash either. For example, let's go ahead and recompile my math. There we go. Oh, darn it. Oh, that's right. I never changed the h. So now that's int. There we go. There. And then recompile everything else. Warnings, 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 right? But now when I run it, I get 0, 0 for roots because it never actually computed anything. Remember, what I'm doing right now is I am passing in null pointers. So what happens is we get to this line, and I don't do the dangerous stuff down here. Instead, I return 37. So I can write code to take advantage of that now. Int error code is equal to that. And instead of printing out the roots, I can ask, is the error code, if the error code is equal to, what was it again? 37? I'm glad you remember that, right? Because I don't remember that. Printf. And what's the issue here? Some bad memory going on, right? Right? And then otherwise, else will print out the actual roots here. Right? Now we're handling the error. Right? Some bad memory going on here. Right? Well, you can check to see if there's another error code. Else if error code is equal to, what was the divide by 0 error? Was it 38? Else. So that's why I did random numbers, because I'm not going to remember them. Was it 38? We're going to have to go and check. Okay, it was 38. Okay. Should I be using these magic numbers? Nope. What should I be doing instead? Either one thing that we've looked at so far are macros, right? But we're going to look at another way of doing this starting on Friday. Right? But else if 38, then print out, what was it again? Divide by 0. Right? You have a linear function, not a quadratic. Doof. Right? So we can still help them out. Right? A is 0, but then we have B and C. How can I solve the linear equation now? Right, what we have here is, I'm not going to be able to do that in my head, bx plus c is equal to 0. So it's negative c over b. There we go. All right. So printf solution is %f and the line negative c divided by b. All right. No integer truncation there, but what else could go wrong? Another divide by 0, right? So we'd have to have another if-else-if check there. I'm not going to go that far, right? So that's, and then what's the other thing that could go wrong? Yeah, it's a printf. I haven't learned complex numbers. Sorry. There we go. There. What was that error code again? Okay, thank you. I did it on purpose. No, it's wrong. We were wrong. It is 13. All right. So let's go ahead and try to capture that. I haven't learned complex numbers yet. I can make B really, really small, I guess. There you go. I haven't learned complex numbers yet, sorry. All right. Okay. Now, when we actually go through this more formally, I'm going to rearrange this. Null pointer checks should actually be the very first thing you do always, right? Because if you've been given bad memory, then there's nothing you can do. Don't bother looking at anything else. So I'm going to move those to the top. The other thing is, well, okay, null pointer checks are good, but what if it's pointing to a random memory location that doesn't belong to me? I want to check that too. You're out of luck. There's no way of doing that, right? Unless you're doing systems level programming and actually operate and doing something in the operating system. To my mind, there is nothing in the C standard. There is nothing in any compiler that you can, check for random memory locations that don't belong to you. Instead, you'll be running a debugger, and you'll be detecting what's going on there. Right? Okay. And second thing that we're going to do when we come back is we are going to be changing these numbers. Right, to human readable formats. For example, what's going on here? Well, this is a complex root error. That's so much better, right? Instead of remembering that random number. So that's what we'll do on Friday. Remember that there is that event on Thursday, tomorrow, that you can go to and meet some employers. But otherwise, any questions? Okay, then I'll see you on Friday.